Welcome to SS2 Computer Science, Term 3, Week 4. Sorting algorithms arrange data in a specified order, usually ascending or descending. Sorting is one of the most fundamental operations in computer science. Sorted data enables binary search, makes data easier to understand, and improves the efficiency of many other algorithms. Today we study three important sorting algorithms: bubble sort, quicksort, and merge sort. By the end of this lesson, you will trace through each algorithm step by step, understand when to use each, and analyze their time complexities. Let us begin. What is bubble sort? Bubble sort is the simplest sorting algorithm. It repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order. After each pass through the list, the largest unsorted element bubbles to its correct position at the end. Why it is called bubble sort? The larger values bubble up to the end with each pass, like bubbles rising in water. Algorithm for bubble sort on array A of length n, for I from 0 to n, 2, n, 1 pass is needed at most. For j from 0 to n, 2, I, inner loop shrinks each pass, n is already sorted. If A greater than A, swap A and A. Let us trace on A equals, pass 1, I equals 0, compare A equals 64, A equals 34, 64 greater than 34, swap, compare A equals 64, A equals 25, swap, compare A equals 64, A equals 12, swap, compare A equals 64, A equals 22, swap. 64 is in correct position. Pass 2, I equals 134 and 64 now in position. Pass 3, I equals 225 now in position. Pass 4, I equals 3, no swaps needed, array already sorted. Time complexity, worst case, O, n superscript 2, when the array is in reverse order, must do n times, n, 1/2 comparisons. Best case, O, n, when the array is already sorted, O, with an optimization flag. Space complexity, O, 1, in place, no extra memory needed. When to use bubble sort, only for educational purposes or very small arrays, too slow for large data. What is quicksort? Quicksort is a divide and conquer algorithm. It works by selecting a pivot element and partitioning the array into two subarrays, elements less than the pivot, elements greater than the pivot. Then it recursively sorts each subarray. It is called quicksort because it is typically very fast in practice. Algorithm, quicksort, A, low, high. If low, high, pivot underscore index equals partition, A, low, high, quicksort, A, low, pivot underscore index, 1, quicksort, A, pivot underscore index plus 1, high. Partition function, choose A as pivot, I equals low, 1, A index of smaller element, for j from low to high, 1, if A equals pivot, I plus plus, swap A and A, swap A and A, put pivot in correct place, return I plus 1. Let us trace on, low equals 0, high equals 5, pivot equals 5, A, pass through, j equals 0, A equals 10, 5, no swap, j equals 1, A equals 7, 5, no swap, j equals 2, A equals 8, 5, no swap, j equals 3, A equals 9, 5, no swap, j equals 4, A equals 1 equals 5, I become 0, swap A and A, put pivot, swap A and A. Pivot 5 is now at index 1 in its correct final position, now recursively sort, left of 5, and right of 5. Pivot choice, last element, simple but poor for nearly sorted data, first element, median of 3, common practical choice, random element. Time complexity, average case, O, n log n, fast, worst case, O, when superscript 2, when pivot is always the smallest or largest element, bad pivot choice, can be avoided with good pivot selection, space complexity, O or log n, to call stack space for recursion. When to use, quicksort is one of the most commonly used sorting algorithms, fast in practice due to good cache performance, preferred when average case performance matters. What is merge sort? Merge sort is another divide and conquer algorithm, but unlike quicksort it always divides the array exactly in half. Steps: divide, split the array into two halves. Conquer, recursively sort each half. Merge the two sorted halves into one sorted array. Key insight: merging two sorted arrays into one sorted array is efficient. Then. Algorithm: merge sort A. If len A equals 1, return A. The base case, single element is sorted. Mid equals len A, //2, left equals merge sort A, right equals merge sort A, return merge left, right. Merge left, right result equals I equals J equals 0, while I len left and J len right. If left equals right, result.append left I ++, else result.append right J ++, add remaining elements, return result. Trace on, divide, and, divide again, merge and, merge and, merge and, compare 27 versus 3 take 3, compare 27 versus 43 take 27, compare 38 versus 43 take 38, take remaining 43. Time complexity, all cases, O n log n, guaranteed, never degrades to O n superscript 2. Space complexity, O n, needs extra array space for merging. When to use: when guaranteed O n log n is required, quicksort can degrade, sorting linked list, merge is efficient for linked list, external sorting, when data is too large to fit in memory, merge sort can sort data stored on disk. Stability: merge sort is a stable sort, equal elements maintain their original order, quicksort is typically not stable. Bubble sort is stable. Comparison of sorting algorithms: bubble sort, time O n superscript 2, worst/average, O n best, space O 1, stable, simple but slow, used for education or tiny datasets. Quicksort, time O n log n, average, O n superscript 2, worst, space O log n, not stable, typically, fast in practice, most commonly used general purpose sort. Merge sort, time O n log n, always, space O n, stable, best when stability or guaranteed performance needed, used for linked list and external sorting. Two other important sorts: selection sort, find the minimum, place at front, repeat, O n superscript 2, always, simple but slow, not stable. Insertion sort, build sorted array one element at a time, O n superscript 2, worst, O n best, very fast on nearly sorted data, stable, good for small arrays and as final step in hybrid sorts, like TeamSort. Python's built-in sort, TeamSort. Python's list.sort, unsorted, use TeamSort, a hybrid of merge sort and insertion sort, O n log n, worst case, very efficient for real-world data. WAEC questions on sorting: trace bubble sort on a given array step by step, write pseudocode for bubble sort, compare sorting algorithms by time complexity, explain what a stable sort is, describe the divide and conquer approach of quicksort and merge sort, state when you would use each algorithm. Key points: sorting algorithms arrange data in order, ascending or descending. Bubble sort, compare adjacent pairs, swap if wrong order, largest bubbles to n each pass, O n superscript 2, stable, simple but slow. Quicksort, choose pivot, partition into and subarrays, recurse, O n log n, average, O n superscript 2, worst, fast in practice, unstable. Merge sort, divide in half, sort halves recursively, merge sorted halves, O n log n, always, O n extra space, stable, guaranteed performance. Divide and conquer, quicksort and merge sort both use divide and conquer strategy. Stability, stable sort preserves order of equal elements, bubble, merge, insertion, quicksort typically not stable. Selection criteria, quicksort, general purpose, average case fast, merge sort, guaranteed O n log n, stable, linked list, bubble sort, educational only, insertion sort, nearly sorted data or small arrays. WAEC, trace algorithm step by step, write pseudocode, compare by complexity, explain stability, know when to use which.